Ladies and gentlemen, welcome to the core of everything. Today we're going to be talking about hydrogen. Hydrogen is the most abundant element in the universe. It's 14 times lighter than air, but it's been considered an alternative fuel source and is used in industrial processes and in fuel cells to generate electricity and power vehicles, and it's even been used to power electrical systems on spacecrafts. In a fuel cell, hydrogen and oxygen will combine, which produce an electrical current. So there's no greenhouse gases, and the only byproducts of that are heat and water. And the potential for hydrogen storage reaches a scale of terawatts, which is trillions or 1 million megawatts hours of energy globally, which is far exceeding the foreseeable demand. The question is, where is it found? How can it be produced? And how can it be stored in the ground for later use? So yeah, welcome to this episode. We're taking a light-hearted approach. Anything to add, Mark?
No, I don't think so. I was only slightly disappointed that you didn't say good morning, and then we could riff off of that we're not actually in the same time zone.
Oh, yeah.
But actually, I guess you wouldn't say that on a podcast anyway.
No. We're currently doing this remotely on Zoom, so the sound quality might be a little bit different. I've got a job at Columbia University in New York, and Mark is plugging away at his PhD in London.
The slog continues.
Yeah. But we're still going to manage to try and get as many episodes in as we can. Whether that means doing a podcast episode at 7 a.m. for me or 1 a.m. for Mark.
We are committed to our fan base.
To our very small but loyal fan base. Let's get cracking. Okay, so when we're looking at hydrogen being produced as a fuel source, there are actually something called the colors of hydrogen, and that's not their appearance. It's based on how they're produced. So on Earth, hydrogen is rarely a gas. It actually needs to be separated from other elements, and we can do this through various techniques, but it also happens naturally. So we produce hydrogen using heat.
Yeah, and there's a few different colors that we've got, which I'm going to give a quick rundown. So note that these colors aren't what the hydrogen actually looks like. Hydrogen, at least when it's in gas form, is a colorless gas, but these are just names that are given to different types of hydrogen. So you've got gray hydrogen, which is the most common, and this is generated from natural gas, typically methane, by steam reforming. So it's basically reaction with water at high temperatures. Methane has 1 carbon atom and 4 hydrogen atoms in it. So when you put it through this reaction at high temperatures, kind of up to 1,000 degrees, it releases hydrogen. So that's our gray hydrogen. We also have black or brown hydrogen. Rather than using methane as our kind of fuel source to produce hydrogen, here we're using coal instead, and we generate the hydrogen through a process called gasification. The problem with this one is it has very high carbon dioxide and carbon monoxide emissions. So it's a less good option.
But not to worry, because now there's blue hydrogen as well.
Indeed, blue hydrogen. This is carbon neutral or low carbon. So we're still using steam reforming, but in this scenario, we're capturing the products, the kind of carbon-based products, particularly carbon dioxide, and storing it underground using sequestration. We've talked about this before on the podcast, so check out our episode on carbon capture and storage. It's a gas. And then we also have green hydrogen. So green hydrogen is clean hydrogen. It's a beautiful rhyme, isn't it? Green is clean. Well, someone must have used that in some political ad. So this accounts for about 0.1% of total hydrogen production. So pretty minimal. It uses renewables like solar and wind to split apart water, so H2O, 2 hydrogen atoms, 1 oxygen, into those constituent parts. And that process is called electrolysis. So we use electricity basically to split water molecules. So this is really helpful because it means that when, for example, there's no sun or no wind, so we can't use this renewable energy, then we've got this stored hydrogen ready to be used as a green fuel. And then finally, we have white hydrogen as well, which is hydrogen produced by natural processes.
Yes, exactly. And these natural processes, because water contains hydrogen, obviously H2O, interactions with water and the minerals in the rocks can create or release vast quantities of hydrogen. And one of these processes that's renowned now for generating hydrogen is called serpentinization. When water mixes with igneous rocks. So stuff like peridotite and dunite, these rocks contain a lot of olivine. And when water interacts with minerals like olivine, it forms a serpentinite, and that releases hydrogen. And they're called serpentinites because these rocks they're this sort of snake-like scaly appearance on the surface. And they're found in a lot in something called ophiolites, which can be found in Oman and the UK actually, and most notably Cyprus.
If you go down to the Lizard Point down in Cornwall, they've got lots of little like statues and things like that made out of this serpentinite. It's kind of, as Jack said, got this green, typically dark green, I think, and kind of the scaly texture.
Yeah, there's basically preserved pieces of oceanic crust that have, during mountain building processes, been moved up into the mountains from the oceans. So we can see preservations of the geology under the oceans on land. And these represent the deepest part of the crust. So basically little bits of the upper mantle.
Mm.
So that's pentonization. That's one of the main processes. We also have radiolysis.
Yeah, so this is when we have rocks that have radioactive elements in them, so particularly uranium and plutonium. And when these radioactively decay, they produce radiation that can interact with water molecules or water that's bound up in the rock. So we're not really talking about like literal liquid droplets of rocks, but kind of water molecules that are bound up in crystal structures. And this water can dissociate and produce hydrogen.
So yeah, so essentially we've got the H2O becomes OH and H, which makes up H2O.
Yeah, exactly.
Right.
Yeah.
Just on that as well is that I learned that a lot of, if we've got aggregate, which is made of granite, and a lot of buildings are made out of granite, there's actually a lot of radioactive material in concrete buildings. So if you go to the hospital or a library and you're sitting there and you're thinking you've got a headache, it might be because there's radioactive material in the rocks next to you releasing gamma radiation directly into your brain. No, that's not true. But it's only a minor amount of gamma. It's only a minor amount of gamma radiation. Yeah, it's minor. No, you wouldn't be harmed by it. I think there's gamma radiation coming from bananas, so I think we're fine. But it's just interesting to know that there's radioactive material in the buildings around you.
Yeah, that is.
There's also deep hydrogen released from the Earth's mantle and crust naturally, and there's also hydrogen that's released from biological activity and the decomposition of organic matter. So bacteria will be sort of feasting on this, it's called metabolizing nutrients within the ground, and that might contribute to hydrogen production.
Yeah, and I guess like hydrogen is particularly kind of prevalent in that sort of stuff because life is organic and a lot of organic molecules contain hydrogen. Organic means they're carbon based, but carbon quite likes to react and kind of be found with hydrogen as well. I was wondering whether that deep hydrogen, presumably that is locked up from when the Earth formed, when all the kind of the gas and the dust sort of stuck together and just got locked up and trapped in the Earth and they're trying to escape.
Yeah, I wonder if obviously it was all locked up quite billions of years ago, and hydrogen's very light. So I wonder if it has been able to be released. Any hydrogen that was locked up billions of years ago might have already been released.
Yeah, and actually hydrogen is so light that we lose a huge amount of hydrogen from our atmosphere every second, every year. So hydrogen in the atmosphere is diatomic. So that means you've got two hydrogen atoms that are stuck together as H2. And we lose 3 kilograms of hydrogen per second from our atmosphere, which is the equivalent of 95,000 tons per year. And to kind of put that in context, we think we gain about maybe maximum 40,000 tons, but probably closer to 10,000 tons of extraterrestrial dust per year. So we're losing more hydrogen than we're gaining cosmic dust, which probably means that the Earth is getting lighter.
There was an interesting study that was released a while ago. Gosh, I can't remember the exact name of the paper, but it's the idea that hydrogen 2.5 billion years ago, there was this thing called the Great Oxidation Event, where oxygen started accumulating in our atmosphere, and there was a flourishment of aerobic life, which obviously we have today because we all breathe oxygen. So our current atmosphere is 78% nitrogen, 21% oxygen, less than 1% argon, and 0.04% CO2. So only a very small amount of CO2. And there's close to no hydrogen, possibly because it's being removed and leaving our atmosphere and heading into space. But before the Great Oxidation Event, because there was a lot less oxygen, it was more anoxic, which started creating favorable reactions that led to the spark of the origin of life. But it was also much richer in hydrogen. So the idea behind how we got this loss of hydrogen and accumulation of oxygen in our atmosphere, it's been shown, there's a paper with Zano et al. 2013, that the atmosphere became increasingly depleted in lighter isotopes between 3.5 and 2 billion years. And the reasoning is because there was apparently a weakening of the Earth's magnetic field. So as we know, the Earth's magnetic field is, the strength is currently optimum for shielding and supporting aerobic life at the present day. However, these modeling studies showed that a weaker magnetic field can lead to enhanced atmospheric escape of hydrogen to space. And the reason behind that is that if you imagine our magnetic field as a big sort of two, as we've done this before, two ears around the planet, the weaker magnetic fields cause something called polar wind escape from the poles, where the steep magnetic field lines towards the poles, they created almost highways for the hydrogen ions to escape into space. So this idea that there was a weaker magnetic field at that time led to the removal of hydrogen, which meant that oxygen was able to accumulate.
And that's what led to the explosion of life.
Explosion of aerobic life, because there was life before then, but aerobic life. And oxygen may also have displaced methane, greenhouse gas, which contributed to plunging Earth into its first ice age. Because before then, temperatures were a lot hotter. And then suddenly we had this atmosphere rich in oxygen, depleted in methane, which meant that it became an ice world.
Interesting.
So getting back to hydrogen being produced naturally, how is it being stored in the ground? So if we're looking at CO2 sequestration, we were talking about the removal of CO2 from the atmosphere and storing it in the ground permanently. Whereas if hydrogen to be used as a fuel source, we need to be able to store it in the ground, but also remove it and meet seasonal demands. Now, some of the issues of hydrogen is that it's highly flammable and its ignition temperature is very low. And one of the ways we can store it safely is to store it underground in the geology. In principle, it's a very simple process. So either it's already trapped naturally underground, or we have to put it there. And in a 2024 review paper in Fuel, it discusses the potential to not only have white hydrogen, which is already naturally in the ground, but also the potential to integrate green hydrogen, so which is sourced from renewables, into underground reservoirs that can keep the hydrogen there until we need it.
Well, there's a few different ways that we can store things, and this is particularly thinking about fluid flow. And there's a lot of research groups kind of looking at this and how various fluids, including liquids and gases, flow through rocks. So one of them are huge salt structures. These are typically called diapirs. So salt is less dense than the surrounding rock typically. And these can kind of rise up and expand through the crust. They creep up through the crust, a bit like a cake might rise. And they're very impermeable, so they don't let liquids and gases kind of flow through them. They're very good for storing hydrogen, particularly because it's quite light, so it won't escape through it.
Yeah, that is one of the issues, isn't it? Because hydrogen is so light, it means that you need to store it in a geology that's, firstly, there's lots of holes in it, so it has high storage potential, but also it has a seal above it, like a lid of geology above it. That means it won't just slowly escape to the surface. And because salt is so impermeable, so what you'd have to do is you have to drill into the salt, inject the hydrogen into the salt, and then it would be actually stored there. But that might involve us drilling into the area rather than the geology itself being perfect.
Yeah. And I guess there's issues with this as well, because if you're, for example, putting fluids underground or putting hydrogen underground, then you might cause some kind of deformation in the rocks. So that could be brittle, like faults, where that could generate kind of micro earthquakes, or you can also get ductile deformation, so producing folds. So kind of just deforming the ground and potentially causing issues for kind of whatever's on top of it. So you really need to have a good handle of what the geology is doing before you do this kind of thing.
Yeah, exactly. One of the benefits of salt is that one thing you don't have to worry about, which you might have to with alternative areas, is that it's very unreactive to hydrogen. So we'll talk about it a bit later, but hydrogen reacts with minerals in the rocks, which could produce harmful, toxic liquids and gases. So Because salt caverns are very unreactive to hydrogen, it means that they're a great place to store hydrogen, but also reduce the loss of usable hydrogen from chemical reactions. So the potential hydrogen for fuel remains quite very high, and the fact that it's very impermeable, so it stops it from leaking. But salt typically has low storage capacity because there aren't loads of salt diapers knocking about. And so we're looking for alternatives. And so there's been a big shift recently towards aquifers, so storage of where natural geology stores water, and depleted oil and gas reservoirs, ones that have been exploited already, but we know that they're capable of storing gas for millions of years. And so we can repurpose them for hydrogen storage.
What's
And
the lifetime on these kind of things? Like how long can we keep hydrogen? Like is it indefinitely?
that's massively dependent on the geology that we have, the different kind of minerals that are there, that what the reactions take place. With CO2, you're looking at storage retention rates for hundreds of years. I don't think it's the final solution with CO2. I think it gives us enough time to find the final solution with removing CO2 from the atmosphere, or at least produce more effective means of renewable energy. With hydrogen, it's a very seasonal thing. So we don't have to store it for that long. You just have to store it for long enough that you can meet seasonal demands.
Right, okay.
And so with aquifers and depleted oil and gas reservoirs, you've got to think of the rocks as like a sponge, where each hole of the sponge is something called a pore space, which is a tiny little gap between sand grains in a sandstone, for example. And when you have that with an impermeable seal, a lid above the geology, you have potentially very high hydrogen storage potential. In aquifers, the hydrogen will dissolve in water to some extent and be stored in the pore spaces or little cracks in the rock. And in depleted oil and gas reservoirs, which have been proven to store oil and gas for millions of years, an issue might be that it reacts with sulfur, because a lot of these hydrogen reservoirs are rich in sulfur, which produces hydrogen sulfide, which is quite toxic and actually quite acidic. So not only is hydrogen being lost through chemical reactions, but this is also corrosive, hydrogen sulfide, for infrastructure and could be quite damaging to the seal, the impermeable seal above the rock as well.
Oh, so this leads us on to some of the issues we have with hydrogen storage. So one of them is leakage. So as we've said, hydrogen is very light. It wants to escape up out of the ground. And so it has the potential to seep through the rocks and escape. But one of the things we can do is reuse old hydrocarbon reservoirs and therefore the infrastructure that's involved with that as well.
But if we're seasonally removing and storing hydrogen over and over again, that could actually affect infrastructure integrity, and the pressure in which you're storing this amount of hydrogen could have an impact on faults within the rock, which is basically large cracks within the geology.
So I guess CO2 is a bit better because we can just put it in and leave it and not have to kind of disturb things.
And if you're looking at storing at shallow reservoirs, you have this whole, because it's lower temperatures, you have this whole dynamic of bacterial influences. So bacteria, as I say, they can feast on the hydrogen and produce things like hydrogen sulfide, or at least it can be very degrading to the hydrogen and ruining its potential. So you are really looking at deeper deposits then, which reduce the amount of, again, viable solutions or viable geology that you can store hydrogen within. But this is being done already. So there is hydrogen being stored underground. Because of the potential using it as a fuel, I went to a conference the other day on hydrogen and natural hydrogen, storing it. And it felt very much like there's an industry rush, very similar to the oil rush in the 80s, where lots of companies are looking to jump the gun on trying to find a hydrogen deposit naturally that they can exploit. It feels like a lot of back engineering, like there's a battle between almost the tortoise methodical element of science and the all guns blazing hare of business. And it's finding that slight balance between the two, where we should know enough about the science to be able to generate hydrogen, but we should also be aware that we need to find solutions quickly.
I guess the engineers are caught in the crossfire of trying to implement what everyone wants.
Yeah, there are still gaping holes in some of the hydrogen exploration in terms of we don't actually quite know what's going to happen underground. when you put hydrogen in there, it's also very light. So we've got to know about which geology is suitable, what thickness of the sort of lid, the seal above the geology is required to store the hydrogen there. But it does look all promising. It's just feel like there's a lot of back engineering. But anyway, there are examples of hydrogen being stored in salt in the UK and the USA, and that's been operating for decades. Obviously, the problem is the amount of sufficiently thick salt layers that you see around the world is rather restricted. But a paper by Tarkovsky in 2021, it analyzed these different storage mechanisms for hydrogen. And the first, I don't know if you can guess this, but the first salt cavern used for hydrogen storage in the world was in.
Haven't we talked about salt or like caves and caverns before? And I wasn't one of the largest ones in Indonesia, something like that.
Close. It was in the UK, in Teesside. So
Teesside, up in the north.
Shout out to Middlesbrough,
Yeah.
and the other places in the northeast of England. Yeah, and it first opened in the
Wow.
1970s and is still
Gosh.
operational. So hydrogen has been storing since the 1970s, although we didn't know much about it. Subsequently, there's been multiple salt caverns used from the 1980s onwards in the USA, including Texas, and there are several more storage sites for pure hydrogen used by the Russian aviation industry. And there's also mixtures of hydrogen and coal, which have been stored in salt caverns in Germany. In terms of depleted hydrocarbon reservoirs, most appear there are potential areas rather than actual case studies, but maybe a more extensive literature review needs to be considered there. And aquifers, there is gas storage in the Czech Republic and in France. So it is happening.
I had no idea this has been going on for so long.
Yeah, neither did I, to be honest. I think it's time for our weekly segment, What in the World?
So for this week's What in the World, it's tenuously linked to geology, but it is definitely linked to hydrogen. So during the US Civil War, so in the kind of early 1860s, there was a guy called Thaddeus Lowe. He was an inventor and an aeronaut. So kind of like an astronaut, but I guess an astronaut for the atmosphere rather than for space.
You mean when did the airplane get invented by the Wright brothers? When was that?
Early 20th century? Was it like turn of the century?
So maybe he was like helping develop a helicopter, the first helicopters or something.
Yeah.
Sorry, Thaddeus, go
on. And importantly, balloons. He was trying to do the first transatlantic hot air balloon flight. And just as he was planning to kind of do this, then the Civil War kicked off. So he was like, well, how do I still get to fly my balloons and do my science and kind of pursue my passion? Well, we could use these in warfare. And so the idea was that these balloons were used for reconnaissance missions in battles. And this led to Abraham Lincoln establishing the Union Army Balloon Corps. So these were balloons that were filled with hydrogen, and they would send them up to observe enemy troop movements, look at the battlefield, work out where kind of artillery was, things like this. And what they would do is when they were up in these balloons, they could telegraph to people on the ground information. So typically it kind of led to these aeronauts taking up army officials with them who would kind of make all the notes and then send it back down to the ground and inform what was going on. There were a couple of scenarios where Lowe went up in his balloon and got caught in a storm. Obviously, if you're in a hot air balloon filled with hydrogen, we said it's got quite a low ignition temperature. So the tiniest spark of lightning could do you some damage. Fortunately,
might burst your bubble.
Yeah. Love it. So good.
Thank you.
But
Thank you very much.
The kind of link to hydrogen here is that they were filling their balloons with hydrogen, and the question is, well, how were they actually creating hydrogen? And it wasn't by any of the techniques that we talked about. So what they would do is they'd have these big containers on the back of trucks, and they would fill them with iron filings, and then pour in a load of sulfuric acid, H2SO4, and then this is a reaction that you probably learned about in your GCSEs. You know, where you get like metal plus acid. You remember what it gives you?
I did the squeaky pop test for hydrogen.
Did you? Okay. Yeah. So metal plus acid goes to salt plus hydrogen. So you get iron sulfate, and then you get diatomic hydrogen gas that they then put in their balloons.
So they used it in battles, did they? Or did they just use it as a form of communication?
Well, both. So they'd use it in the battle, although I was
because
kind of
it's
thinking like surely the opposition could just shoot the balloon.
yeah. Well, that's the
Surely it's
point.
quite a big target.
It's target practice for them. It's like a
Yeah.
really easy version of clay pigeon
When
shooting,
you see the hot air
where
balloons with the like red and white rings going around them, it's
it's
like a
just a massive,
target.
massive target. Gosh, that's really
So,
good. That's really interesting. What was his name? Thaddeus Lowe.
Thaddeus
Thaddeus.
Lowe, presidential appointee,
Thaddeus Lowe.
aeronaut, and inventor.
That was excellent. That was
Thank you.
excellent. And that concludes our episode. I guess I think it's worked well on Zoom. I think we've done okay. I think
Yeah.
we've done okay. And it's time for us to say hydrogen and goodbye. Bye, everyone.
Bye.